Okay, so then, where are we? Okay, so we're doing the quiz, and we're now on question 1C. So it has a phenol group, and then that's reacting with CH3 with a Cl on it, and AlCl3. So we can just start step by step and kind of determine what's going to happen. So this is just clearly alkylation. So you're going to get your phenol group with a methyl stuck off of it, basically. And you should know the mechanism for that by now. If you have any questions, let me know. Secondly, it says that there's going to be bromination. So for that, we're just going to add a bromine. Now, where do we add it? Ortho, para, meta. Um, well, if you look at an alkyl group, it is activating and it is ortho-para directing, as usual with activating groups. So let's just go ahead and put it in the um, methyl, and then you can put it in that position, or you can put it in this position. Now, of course, it's not like you can really tell because I'm just drawing the quick little phenol groups or benzene rings, but I'm kind of just doing that because I just want to make things faster a little bit. And then after that, there is NaCr2O7. So what does that do? So NaCr2O7 basically takes anything, like any alkyl groups, and cuts them off and replaces it with a CO2H. So you just have to take that methyl and change it. So I'm just going to draw the full thing now. So that methyl got changed to CO2H. And the bromine remains in the same spot and doesn't get affected by the NaCr2O7. So this is kind of what we get. There's two options. Um, next. Okay. And then next we have going on to D. So for D, sorry. Okay, so it goes like this. I should just draw the whole thing. Um, so okay, so this is reacting with HNO3, which is basically nitration. Oops, someone's calling me. Yeah. So that's nitration, and then again, the whole question he's really asking here is what group is the most strongly activating, and where is it going to activate it to? Is the whole thing. Um, all right. And so essentially, when we look at this, uh, so Cl is activating, right? Um, as is, wait, no, it's deactivating. Sorry. Yeah, the halogens are deactivating, but orthopara-directing. So it's between kind of these two. The O is, let's see. No, that's actually activating as well. So, yeah, because the O is activating. If you guys look at the thing, it's actually more activating than CH3. So the O is going to be the boss here, and it's going to attach an NO3 to a um, ortho or para position, which can work on either. It really can't go to para in both of those, right? It has to go to ortho. So we're kind of looking at somewhere between this, or this, right? Those are the only options. But because CH3 is also activating, it prefers to go to this one because this is deactivating, so it's more likely to go to the right than to the left. Even though it's in a meta position to that methyl, the methyl is still more activating than Cl. So we'll just end up drawing it somewhere like here. Okay. Next. Okay. So E, we have benzene ring with OCH3 and a methyl para to that. And then this is our, we're going to be doing acylation or acetyl, what do you call it? Alkylation, sorry. So basically what's going to happen is that it's the same thing as usual. You just have to figure out, okay, where on this circle is it going to go? So the most activating portion is going to be the OCH3, I believe, right? Yeah. So that's the most activating. It's more activating than just the plain alkyl at the top. And it's going to direct it towards ortho or para, but the para position is taken, so it's going to go to the ortho position. And so we're just gonna, it's just gonna like attack out here. And of course the Cl has to break off. So what you get is you get, just draw the same thing as before, leave it all exactly the same for this one. But then for the other one, it's gonna be attached to the ketone portion. And then on the other side, it's gonna have the phenol or the benzene. Okay. Question number 2. Again, if you guys have questions, put them in the chat. So for question number 2, it says that there's a cyclized product of this. So it's 1, 2, 3, 4, 5, double bond, methyl, methyl. Okay, so, and this is reacting with H2SO4. So I'm thinking that this is going to be, it's kind of like an alkylation in an interesting way. Or actually, no, it's going to be the double bond is going to be reacting with the H2SO4, something that we probably learned a little bit about before. But anyways, how you can think about it is that, so this is going to end up just curling back onto itself and attaching onto it, because he said it's a cyclized product. So that means we're going to have to form a ring that's not there originally. So what happens is, like, you might want to think about it in terms of mechanism, and I'll explain the mechanism if anyone wants to know. But we just draw our H2SO4. The double bond attacks the hydrogen. Now that hydrogen is following basic mark. So what happens is that you get the hydrogen goes to the right side, which I will show with a little gray, okay, a little gray mark. So now we have 3 hydrogens there. And on the other hand, there's going to be a positive charge here. So this positive charge is basically going to be the thing that drives the ring to close. So all you have to do is imagine the positive charge attacking the ring right here. And then what happens is that this is going to close. So you can go ahead and you can kind of like count. So there's going to be 1, 2, 3, 4, 5, 6. 6 members in the ring, okay? Notice how I counted the 2 ones that are going to be involved in the ring that are on the other ring as well. So now I know it's just going to be like 2 cyclohexanes right next to each other. And, or no, there's no benzene there. But we have to, oh, I forgot this, okay. So we have to make sure that our methyl's in the right place. So this one that's attacking right here has 2 methyls coming off of it, this one and this one. So I'm going to show that. Wait just a second. Yeah. So I'm going to show that by putting 2 methyls off of that. And then there's another methyl on this one. And that's your answer. Okay, now we have a retrosynthesis, and the retrosynthesis are definitely a skill in this course because they're a little bit harder than last semester. So, but there's definitely ways to think about it where you'll probably get it right every time. Okay, so one of the keys with this is like figuring out, okay, so what groups got added onto here? Well, we added an alkyl group and a nitrate group, right? So you have to think to yourself, okay, so which one got added first? Also, what position are they to each other? So these are meta to each other. And if you look at NO2 on your list, NO2 is, where is it? Very, very, very strongly deactivating. It's the most deactivating thing on there. It is meta-directing though, but it's very, very deactivating. So what would be a better solution to this is to, so you could just put the NO2 and then do like an alkylation. But what would be a better solution is to go ahead and start with what do you call this, acylation? When it's like a ketone like this? Or Friedel's Craft, yeah, acylation. So we're doing acylation first. This is like a way better solution, by the way. So what you do is that's gonna get attached on there. And then after that, we're just going to do the NO, because now if you look at like this group where it's like a C with a double bonded O, that is, it's still deactivating, but it's much closer to being activating. Like it's less deactivating than NO2. So what happens is that we should just attach our NO2 on here now. So HNO3, HOSO4. So this is going to be meta-directing. So it's perfect. You just have to make sure that your logic works, okay? That it's meta-directing, that it's as activating as possible. Finally, because we need an alkyl and not that ketone group, we're just going to do Clemenson to get rid of that. Okay, and that's it. So that's why some of you might be like confused when you first saw it.
Fatima,
Oh, yeah?
just out of curiosity, can you do Clemenson before you add the NO2? Like, does it matter what order that goes in?
Yes, it does. It matters what orders that goes in because if I had done Clemenson first, then it would have been an alkyl group, and alkyl groups are ortho-para-directing,
Oh, okay. Thank you.
right? So that's why it's really important that there is a system to doing these retrosynthesis that takes a little bit of getting used to. Okay, so someone asked, can I repeat how to determine which part is added first? Okay, so I look at these two options, right? And NO2 is extremely deactivating. And on the other hand, the alkyl group is definitely more activating than NO2, but there's an issue. The alkyl group is ortho-para-directing, right? So I know that I'm not going to just add my alkyl group and then do nitration. That's impossible because if I added my alkyl group first and then did nitration, it would go to ortho-para. But what I'm saying is that when you have a situation exactly like this, what's a good option is to start off by acylation, and acylation is more activating than NO2. So this group right here is more activating than an NO2 group. And so the logic that goes through this retrosynthesis right here is foolproof. First, I added an acylation. Acylations are meta-directing, so that works. And then Clemenson gets rid of that. So it works on a better level than just going for the NO2 first. If you were to go for the NO2 first, because NO2 is meta-directing, so you could have done, you could have done, but also we don't even know how to do a straight alkylation of a chain. Am I right? Because of rearrangements. Is that correct? Sorry guys, it's been a while, but I don't think we can do alkylation of a straight chain.
We can't because of rearrangements.
Exactly. All right, so yeah, so a rearrangement will occur, so that's kind of another way that you know. But so there are some situations where he will take it if you give him an NO2 first and then do the alkylation. But he will take off a few points for not being like the perfect retrosynthesis or the best retrosynthesis. All right, finally, question 4. So for question 4, he says, what two products make up a ring, cyclohexane, double bonded thing, a triple bond there, and OH. Okay. So whenever we see an OH, we think to ourselves, we know that like this must have come from like a ketone. I mean, that's this exam, you know? So what would happen? Well, another thing we notice is this group right here. This might be a little new to you guys because I think this was like last lecture. This group right here, we can kind of bring it in as which I believe we kind of did this last semester. You can have this kind of, and that is almost like a nucleophile or something. So what happens is that, let's say I start off with this, like a ketone, then I attach this onto the carbon with the ketone, that would lead to exactly this answer. Okay. Any questions? All right. Okay, so that's that for this quiz. Okay, can I explain this one a little more? Okay, so how do I explain this? Okay, so whenever you see like an alcohol, what happens is like if you can imagine, yeah, I'm gonna just draw this out a little bit better. If you can imagine, here's a carbon, here's a ketone, right? And let's say that I took, I don't know, let's say that I took a Br and I attacked this carbon right here. What would happen? So what would happen is that we have this with a BR on it. But there's an issue. What's the issue here? Can I get it in the chat? What's the issue with what I've just drawn here? Breaking octet, exactly. So that means that this is forced to let go of one of its bonds, and it becomes an OH. So that's how you can think of it, okay? So when something attacks that carbon next to a ketone, that ketone turns from a ketone into an alcohol. So similarly here in this new situation, where we see this, and we see that it's already an alcohol, we think to ourselves, hey, that could have come from a ketone, and something attacked the carbon of the ketone, and that turned it into an alcohol. So if you think that this might have come from something like this ketone, and it got attacked by this portion right here. So a triple bonded carbon came along and attacked this, and bonded to it, and therefore broke the octet and broke one of the bonds from the O to the carbon. Does that make sense? Okay. Okay, so that's it for the quiz. And I'm going to go on to the lecture from the 28th. Okay. So I'm just going to be going through this real quick, looking for some things to bring up that are important to know. So a lot of this stuff we just did. But one thing I want to point out, like one more time, like everyone please pay attention. When you have a benzene ring and it's attacking, this is a good example he has right here, and it's attacking something that it's attacking a ketone, a carbon from a ketone, right? You have to break this off, okay? So the first thing that happens, I'll explain this in a little more detail. So the first thing that happens is that I have phenol is attacking, so the first thing that would happen is that off. It doesn't. Oh, it's just up. Can you guys hear noise? Can you guys hear me now? What's happening? That was so weird. It was like I could hear like a little noise coming out of the iPad. Yeah. Okay, so can you hear me better now? Okay. Yeah, so I heard like a little noise coming out of the iPad. I have no idea what that was, but if I hear it again, I'll know that you guys can't hear me. God, so weird. Okay. So what I was saying is that some people are going to be tempted to think that if I attack here, then I need to break this octet and change it into an OH. No, that's not the case if you have something that can easily leave, like an O or a Cl or something like that, right? So the first thing you do is if you really leave the molecule, you do that, which is this step right here. Next, let's continue this scenario. And let's say that now I have this, attach to this, right? Which is the result of what would happen after this above scenario. Now let's say that I wanted to attach this to one more. Or no, sorry, say that I wanted to bring in another phenol. So this phenol would also attack here, right? And what happens in this case? Well, there's nothing we can break off. So this is the thing that breaks, one of the bonds of the ketone. So I just want to illustrate the difference between the first time you do it, the second time you do it. Is the first thing you need to ask yourself is there something that can break off? Okay, so that's our answer. Does everyone get this? About like when you break something off versus when you just turn it into an alcohol? Okay. All right, let's continue. So, all right. Okay. Um, Let me know if
I
if
have
it,
a question. I'm sorry. For that alcohol, is that a methyl next to it or
yes, that's a methyl because right here, this is a methyl.
okay, thank you.
Yeah, no problem. Okay. Next, he just has some more examples of stuff like this, and like you guys are already pretty good at this, I think. You know, recognizing when something's aura versus meta or para directing or whatever. Um, there's just a lot of that, so I think I'm just gonna skip. Let's do a synthesis problem from this lecture. Um, so here's one. Um, and I want to get you guys to participate in the chat and tell me how to do this. So, just tell me, like, take like 2 minutes. I'm not gonna, rush you guys at all, and think about how you would want to set this up. Just look at the orientation of those two things to each other, and then tell me kind of the basic steps that you would use. You need to think about which ones are more activating than the other one, and where would they direct you. Any responses? All right, I'll give you like um I don't know, 1 more minute. And type your answers into the chat. Okay, I haven't gotten any response in the chat yet. Are you guys working on something or no?
I'm working on something. I don't think it's a very good something, but I'm working on something.
Well, that's good. Yeah. This one's a little tricky, but I'm gonna go ahead and just start explaining it real quick. So, what we notice about this is that what must have happened here is we must have had two steps of what? The same kind of substitution.
Well, it's acylation, I think, right?
Yeah. So we know that there must have been two steps of acylation. How do we know this? Well, because like I mentioned before, you can't do alkylation of a chain. There would be a rearrangement there. Oh, you guys are messaging the Fatima that's muted. Okay, that would make a little bit more sense because I hadn't gotten like a single answer from anyone. Okay, so yeah, just send your answers to the Fatima that's muted. And I'm just going to continue talking about some of the things that we know. So this is clearly acylation, right? And then this must have also been acylation because of how it's a chain. So I know there's two steps of acylation, but the question is which one came first, this one or this one? Well, if we have a C with an O attached to it, it is pretty deactivating, right? It's deactivating. So we don't want to start with this one. It's not only deactivating, it's also meta-directing. So we need to start with that one, the chain. So we're gonna start by acylating a chain on. So you guys already know the step, so I'm just gonna there. That's the result of the first step. Then what do we need to do? We need to cut this off before we put this on, because if we left it like this, it would be deactivating and meta-directing, but we need it in the para position. So that's why we're going to do Clemenson, which will give us just the chain first. Then there's the final step. That gives us the acylation in the para position. Any questions?
I have a question.
Yes.
What are we, I mean, I'm really bad at synthesis, but like, what are we using to get the first step again?
Oh, yeah. So the first step is basically, because I just kind of did like really messy synthesis because I didn't go through the whole thing. But the first step is just going to be, it's going to be like that, and it's going to have an O there, a Cl here, and it's going to be with AlCl3. So
All right,
yeah,
that's what I
it's
thought.
just
Thank you.
attaching. No problem. Okay, any questions? I know this one seemed really tricky in the beginning, but it's actually not that bad, right?
I have a
It's a
question.
process.
Right.
Uh-huh. Go ahead.
It's not. It's kind of related to this one, but it's more like general notes. How do you know when to do like Wolf reduction or Clemenson reduction? I mean, do they kind of give like the same product? Does it really
Yeah,
matter?
give the same product, and the thing is that in this class we prefer Clemenson.
Okay.
Because we can just write Clemenson. So yeah, but you have to know what Wolf looks like in case he gives it to you. But I would suggest in your synthesis just stick to one and make your life easier.
Okay.
But know what the Wolf reduction is just in case it comes up in a question.
Okay. Thank you.
All right, any other questions? Okay, I'm gonna move on to the next synthesis that he has right here. So this one has, okay. So this one is one of the more challenging ones for sure. Because we attach so many things and we really need to make sure that it's coordinated with each other. So looking at this, first off, one thing you'll notice is that the nitration can't have been the first step. This is like a big thing that you should notice right away because firstly, there's, ooh, Okay, that's a little bit weird. Sorry, this is wrong. Okay. So NO2 is the most deactivating thing that we have. So NO2 should really, it's not gonna be, it could be in the middle and it could be at the end, but it's not gonna be the first. And I'll show you guys why. So between CL and BR, we're noticing that, so BR and CL are meta to each other, and NO2 is para to to BR. So what kind of patterns are you guys thinking of? Like what kind of pattern? Like what kind, or just list them off, like BR, CL, NO2. Which one comes first? Which one comes second? Which one comes third? But I want you guys to notice the meta relationship between CL and BR. And then how BR and NO2 are para. So I'll tell you guys, yeah. So some people, everyone knows that NO2 isn't gonna come first. Some people are gonna say, okay, it should be what is it that I'm getting here? BR, CL, and then NO2. And then some people are gonna say BR and then NO2 and then CL. And out of all of these, this one is the best because NO2 is meta directing. So that's going to help like the CL get into that position. What would happen? I'll show you guys why it's not the first option. What would happen if I had a BR here, a CL here? Where would the NO2 go? The NO2 would not go here. It would prefer to go, it would really be quite a mess actually. It would why would it prefer this carbon at all? When you do your synthesis, you want it to be as clean as possible. And this is not a clean reaction at all. So we're gonna go ahead and so this is just some of the basic things you can kind of sketch out with your pencil on the side before you start doing the retrosynthesis to figure out what steps are best. So here we're gonna go with BR. We're gonna choose the bottom path. We're gonna follow that. So I'm gonna move this up here. So the first step we're gonna do is BR, so bromination, and we'll just attach the BR here. Then after that, we're gonna do nitration. And how that'll help us is because nitration is meta-directing, so we'll certainly end up in this position. There's really no other option for it. I mean, it'll either go to, here, I'll show you guys. So nitration at this point, it's either, so for the nitration step, it's definitely gonna go to the para, right? I mean, you might get some in the ortho, but that's not that much of a mix. And then after that, for the CL step, it's only going to go to either this position or this position, which are actually the same molecule, whether it goes to the right or to the left. Does that make sense? So this is a pretty clean reaction. All right. Someone asked, can I explain why NO2 why you can't do NO2 first? I can't do NO2 first because if I was to do NO2 first, it's just very, very deactivating. It's just not favorable that way. It's not a very energy favorable reaction. So, I mean, NO2 can happen on its first, but this is going to be a really hard step to get it to the next thing. So usually you try to keep, you know, your deactivating things to the minimum where they have to influence your outcomes. Um, and I'll show you a difference here. So once NO2 is there, getting our CL on, which would be the next step, right? Getting our CL. Getting our CL on is going to be really, really like a hard step. Okay. But the way that I did the synthesis above, it's you have your NO2, but at the same time, there's also the less deactivating BR. So this helps that reaction happen better. Where now it's much, much more likely and it'll take much less energy to get a CL on there. Does that make sense? So it's kind of like a comparison of these two steps. In the first one, you only have a very deactivating thing. In the second one, you have a very deactivating and a slightly less deactivating. So altogether, it pulls it more correctly into this spot. Okay, so why can't you do BRCL then NO2? Okay, yeah, so why can't we do BRCL and then NO2? Because if I was to do BR, then CL, that's fine, but this is the issue. How do we add this NO2 onto here? Because what would happen is that where would your NO2 go? Actually, can you speak up for this one? Would it go here, 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 or here? Who wants to volunteer to tell me about the NO2 and where it would go in this situation?
I think it could go in either the one that is 3 away from BR or the one that is 3 away from CL.
Or it could go to the one right next to BR or the one right next to CL. Because, so really all of these positions are very unfavorable. So basically, or they're equally favorable. So what happens is that why would the NO is going to go to either a para position from the CL, which is right here, or a para position from the BR, or an ortho to the CL or an ortho to the BR. But either way, every single one of those positions is meta to something else. Right? Look at each of these positions. If you go, let's say you go para to the BR, well, that's meta to the CL. Okay? Let's say that you go para to the CL, that's meta to the BR. You go ortho to the CL, meta to the BR. Okay. So that's why it would just be all of them are equally unfavorable, pretty much. Or not equally, because there might be a little bit of stereo hindrance at those two, but it would just be like a crazy mix. And so your synthesis wouldn't make any sense if you suddenly end up with it para to the BR, because he'll be like, well, what made it go para to the BR? That's a terrible synthesis. Okay. Next. And again, I just remind you guys, anytime you see like a chain or something that's not tertiary coming off of a benzene ring, then you know that it was acylation first. Okay, this one seems a little complex. Okay, so I said anytime that you see something coming off a benzene ring that isn't tertiary, so if it was like this, or if it was like, I don't know, like this, whatever, those are all going to happen from acylation first because there would be a rearrangement there. The only situation where it could have been alkylation would be if it was a tertiary carbon right there. So if it was like this, whatever, that's okay. This can be alkylation. Or wait. wait, no. Yes, that can be alkylation. Not, wait a second. Yeah. Does that make sense? Okay. So here is a nice little synthesis as well. Do you guys want me to move past this, or do you want me to continue doing synthesis from this lecture? Just kind of like vote in the chat. Do you want to continue synthesis, or do you want to go on to the next chapter? Okay, you guys don't want more synthesis. Okay. So here's an interesting little synthesis that has a few more steps involved in it, so that's really good practice. So we have NO2 and we have this. Okay. So we've only added 2 groups onto this benzene ring, right? We've added an NO2 and an alkyl group. So something that we have to think about is, okay, NO2 is really deactivating and meta-directing. So like there's no way that comes first. It just can't. So we know that this must have come first. And like I said, you can do alkylation in this situation. So it would look like this. So it would have a Cl, and then it would be 1, 2. So that's the thing that we'd be looking at. It would be AlCl3. So that would lead to that little antenna shape coming at the top. From this position, it would probably be best to add our NO2 right now. But I mean, honestly, I don't think you have to. Let me look at the chart. Yes, it's better to add it now because if you look at your chart, the double bonded carbons is a little bit less activating than a straight alkyl. Yeah. So it would probably be better to add the NO2 right now because that's a little bit more activating than later when we change it into a double bond. So let's add our NO2. Okay. So from here, we need to somehow get a double bond there. And so your best option, which is really good to learn for these situations, is NBS. Because what's going to happen with NBS is that you can eliminate through NBS being a good leaving group and all that. So NBS is going to lead to this. And there's a BR here. Okay. You have to, when you're adding NBS, make sure that it will add to the correct position. And like I said, the correct position is something that's benzylic, but also the most stable benzylic. Sometimes there's many benzylic positions, but one of them is going to be more stable than the rest of them. So make sure that your synthesis actually works and it yields a lot. Sometimes when I'm really, really stuck on a synthesis, I just do a synthesis that yields a little less, and I write down so that Dr. San knows that I understand that this is kind of like a low yield reaction, and there's going to be a mixture of products there. But if you're really, really stuck, you're going to get the majority of the points, even if you come up with a low yield one. So from here, then you just have to do elimination with that leaving group. So like this would work, and that would eliminate it. Questions? Okay, next. So now I'm going to draw this last one. Yeah, we have 2 more. Okay, let's just do them both. So here's a benzene ring that turned into a benzene ring with a whole bunch of things on it, which is great. So again, I'm just going to walk you guys through what I'm noticing first. So like the moment I wrote it down, I was like, oh, okay, sorry, not Clemson. That's Na2CR207, that thing, right? So it must have come from some alkyl group before. What else? So again, NO2 extremely deactivating, but it's meta directing, and we have a lot of meta going on here, so we might need it. Is CO2 meta-directing or ortho? Sorry, not CO2. Yeah, CO2H. Yes, it's meta. So they are both meta-directing, both of these. So that's kind of going to work well for us. But this one is really, really deactivating. So I think we should start with probably not the BR. We won't start with the BR because if we start with the BR, then we're going to end up with something para or ortho, right? You guys get that? Why we're not going to start with BR? So between the two, let's just start with the CO2H. So when I say start with the CO2H, I don't mean substitute a CO2H on because that's impossible. We don't know of anything like that. But what we do know is, like I mentioned, Na2Cr2O7. So first, let's get an alkyl group on here. So you can make that any alkyl group you want. That's fine. I'm gonna go ahead and I'm gonna just do like, I don't know. You can really do whatever you want here. So I'll just use the same one that we did before. But as long as it's an alkyl group, it'll work. So that's my first step. Then my second step is I'm going to do the Na2Cr2O7. So when I said start with this group, I meant create this group first. It's going to maybe take a step or two, and then you can start substituting other things in. So this is going to become CO2H, right? So now we're ready to look at, okay, what's going to come next, NO2 or Br? If we go to NO2, that's going to be really, really deactivating. Actually, no. No. It would probably be better to go to NO2 first. Because even though NO2 is very deactivating, it's meta-directing, so that'll help that BR come into this position more correctly. So, yeah, I think that would work. This one is maybe a little tricky. I'm not sure if, like, sometimes the decision to go from one to the other is a little bit more murky. But I think I'm gonna go for the directing thing over here, more likely. So I'm gonna do my NO2 first. So I'm going to put this into the meta position from the CO2H. And then that means that the BR is 100% going to go here. So that keeps it really nice. Okay. Yes, okay, that is definitely the correct answer. You can't actually do BR first. There's a reason that I just realized you can't do the BR first. And why don't I give you guys a minute to think about that? Like, why is it like absolutely critical that your NO2 comes first? Because sometimes it's like either or, but sometimes there really is one answer that's correct compared to the other one. Okay, yeah. So I got the correct answer in the chat, which is that BR is actually more activating than CO2. So the NO2 that we're substituting would be more likely, I'll explain that in a second. Let's just continue. I'll explain like in more detail because I feel like just saying it is going to be a little bit confusing to some people. So once we have our NO2 into the meta position, then we're just going to go on with our BR. And that's like, you know, gosh, my handwriting is so bad today. All right, so why can't we do BR first? Because if I was to go, so first step is just this. And then secondly, we're adding the BR. Oops. Let's say we added the BR to the meta position. Now, here comes the issue. Which one is more activating, this or this? Can I get it in the chat? Can I get like at least like 4 responses? Which one's more activating, BR or CO2H? Okay. Yeah, nice. Oh, okay, yeah. Good participation, guys. BR is more activating. If you just have to go to that chart. BR is more activating than CO2. So, what that means is that BR is really going to influence a little bit more than CO2. And that means that our NO2 would be more likely to go to somewhere that the BR wants it to go. Where does the BR want it to go? The BR want it to go here, here, or here. And the one place it won't want it to go is there. So, overall, I think, yeah, go ahead. Did someone just raise their hand, right? Okay. All right. Well, if you think of your question, just, oh, okay. Oh, okay. So that was an accident. All right. So the one place it won't want it to go is this position. So it's going to be very likely to follow something else. Guys, I'm getting a call now, so let's take our quick 5-minute break right now, and then we'll start back or let's take a 10-minute break. We'll start back at 8:30 and then go till 9:15. All right? All right. So this tells us that the bromine came second. So the first thing that we're going to do is we're just going to attach a benzene ring that has this kind of going on there. And then what happens is that this attaches on, but since there is a ketone there, it's going to make the bromine go to the meta position more successfully. So now we can do our bromination. And I'm recording now, by the way. So at this place, we're going to get a bromine in the meta position. And then from here, we just need to get rid of that ketone. So we just go, yeah, you can do either one, but let me just say Clemenson because that's easier for me. All right, so Clemenson. And that's it. Any questions? Okay. So some people are saying that they want a session on Monday. So I'm just going to go ahead. I know some of you guys are going to be like well prepared for that with just the Sunday and Wednesday, but I will just do a session on Monday, and I might like make it like 1 hour long, like, you know, half of our normal time. And then we can kind of, you know, it can be like a little bit more chill, or if you guys need like specific things, we'll work on that. Okay, so I just finished with the lecture from the 28th, so I'm gonna go on to the 20, or sorry, just a second. I'm gonna go on to the lecture notes from February 2nd. All right. Okay, so this is where we start talking about Grignard and how Grignard works. So Grignard is kind of like, it's kind of like a nucleophile, I want to say. I mean, I'm not sure if that's the correct word to use, but it's kind of like what we did last semester where we had, you know, nucleophiles with negative charges on them. So one of the things that you can just do that, I mean, that, what do you call it? That Dr. San does on this first page is, so JD's saying that Dr. San draws 3 lines to equate Grignards to nucleophiles. Yeah, so you're saying that, yeah, so Grignards are basically nucleophiles, because, yeah. So, let's see. Okay, so what this kind of means though a little bit is that, like, if you have like, because like a Grignard you would typically draw with like maybe an MG on it or something like that, like MGBR or something like that. Those are basically like, you can just ignore the MG and it's like a negative charge. Okay, so if I have like, let's say that this was an MGBR, this is the same as this with a negative charge. So you can kind of just cut that MG off and just imagine it with a negative charge. That's essentially what you're working with. This is the nucleophile, and this is the Grignard. Grin. Oh my God, I've been saying it wrong the whole time. It's Grignard. I've been saying Grignard. Okay. Wow. Okay. Anyways, so you have to use, he's saying here that you have to use aprotic solvents, and so he's just reminding you of two of them. So you can use THF or ET2O. And I would stick to one of those because there are other aprotic solvents, but if you just stick to those, then, you know, you'll be good. Okay. So what do these negative charges do, though? Wait. So they basically, what do nucleophiles do? They substitute, right? So we're just going to be using these Grignard reactions for different kinds of substitutions. Let me find an example. Okay, so here we go. So here, and this is kind of so similar to what we just talked about, which is I think why JD was saying that it's hard. It's because like it's so similar. But here is an example where he has this with MGBR. So MGBR, you can completely just ignore them basically. So this is essentially just this with a negative charge. You can just cut that MGBR right off. Now this negative charge is going to attack the underside of a ketone. And like I mentioned before, this is going to break off. That's the first step. We're not going to go straight to an alcohol. The first thing that's going to happen is if there is something I can break off, it will. And so what do we get here? We get, oh yeah, I just went over this example kind of, but what we get is we're going to get something like this. Okay, so from here, let's say that another negatively charged ring came along, it would attack here, and that would turn this into an OH. So then what you get is you get, like I said before, right? An OH. Like that. Okay? Tertiary alcohol. So we can kind of just apply this over and over to different situations, you know? Something attacks a ketone. The first thing that'll happen is if there is this possibility, something will break off from the ketone. Or if there isn't, this is just to maintain octet, then the ketone will become an alcohol. From that point, you actually can't substitute anything else on. So you can only substitute things onto, like Grignards have to involve ketones. If you have an alcohol in this position, that means you can't do another Grignard to it, which also makes sense octet-wise. Okay, so one thing I would caution you guys is don't ever break off a carbon. So if I had something like this, and I was trying to get this nucleophile to substitute on, don't break off a carbon. You can't break off carbons. You can only break off like CLs or Os that are attached to something else. That's the only thing that I've seen so far. But don't break off carbons or hydrogens or anything like that. Okay. It's all kind of just the same thing. I don't really see much. So I guess one thing worth noting here is how he talks about, he shows this. So if you have like an MGBR, right, which is just this, right? And if I'm reacting that with something like this, with a C and an H, your Grignards don't only have to react with ketones, they can also react with just a hydrogen. So this could grab that hydrogen right there. And what would happen in this case is that now the MGBR is going to be attracted towards this carbon, because this carbon is now going to have a negative charge on it. So what we get is we get just this, and it's normal now. It has no charge on it. Plus, we're also going to get this original thing with the triple bond, but it's going to have an MGBR at the end. Okay. So So it's kind of like a way of transferring, you know, your your negative charge from one thing to another. Um, and like we already know from Chem 1, from Oreo 1, it's preferable to have a negative charge on a triple bond than to have it on a single bond. So that's kind of why that happens. Yeah. And then this can be used for different things. Now we can use this as a substitution. So we could go ahead from here and have a ketone. You know, like if we had something like this, then this could attack here. No, it couldn't. Wait, could it? Yes, it could. No, it couldn't. Let's say there's an H here. Okay. No. Gosh, I'm like back and forth. Okay. Let's say that was like this. I think that's how it could work. Yes. So if this attacked here, then what would happen is that, yeah, this is the only way it can work. Then what would happen is that we would get, this would turn into an alcohol. So we would have the triple bond here, and that would just be attached to the carbon that's attached to an alcohol. Do you guys see that? Because of octet, it needed to have a hydrogen here and hydrogen here. Oh, actually, it could have not been a hydrogen there and hydrogen there. So never mind that. But yeah, anyway, so what I'm trying to say is that we kind of use an original Grignard to change something else into another Grignard, and then we use that Grignard to do substitution. Because a triple bonded Grignard is preferable, if possible. Okay, so now we're going to do this whole pathway thing again, which is really going to be familiar to you guys. Julie, can you explain a little bit more about what you're talking about?
So there's reasons why you can't use Greenyards with protic solvents, or like if you combine a Greenyard with an alcohol, it will just result in like the what's it called, the hydrocarbon that the Greenyard is attached to plus like NO negative with a MgBr or whatever that's hanging around it. I just have a really strong feeling that that's going to be on the quiz tomorrow based
Wait,
on.
can you send me a quick little example over the Google no, sorry, the GroupMe chat?
Sure.
Because I'm
Give me
having
a
a really
second.
hard time visualizing what you're saying. Yeah. Okay. And while you're at that, I'm just gonna let me know when you've sent it, by the way. So I'm just gonna move on to this pathway thing. Did you already send that? I just got a notification. Okay, all right. Never mind. Okay, so we're talking about pathways now because this is something that's gonna be familiar. And I don't know. I don't think it'll be on your quiz. I don't know. It could be, but yeah, it might be on your quiz. Okay, so we have to figure out, okay, so what was the ketone? Where was the ketone specifically? And what got substituted onto it? So, so this could have been, it could have been one or two things. So you draw your two lines. So you draw one here and one here. And I'll call this one A and this one B. So if it was pathway A, that would have looked like benzene, this, and the double bond is here. Okay. And then what happened is that something like a carbon CH3 with a negative charge came and attacked this carbon. And that resulted in exactly what we have above, which is basically an OH here and that there. Or something else could have happened. We could have had the opposite, where it looked more like this. So it was like that. Okay. And what happened is that from this position, it was 2 carbons long, and it came along and attacked here. And that produced the same exact thing. So there's 2 possibilities. And I think both of them are, both of them are possible. Okay. Next. So it's important to recognize that there must have, like, what the pathways could have been. So here's one more that we kind of already did. So I wonder if you guys remember it still. Okay. So, okay. Tell me in the chat real quick, like, what this kind of came from. Just like a quick little description. Julie, what you just sent me, is that because it's protic or what?
Yeah, that's because it's protic.
Yeah, I don't really know about this. I don't really know the answer to this. Maybe it's because I haven't gone through it yet and stuff. But it's interesting because instead of attacking the ketone, it took the hydrogen from the alcohol. Okay, good job, guys. Yeah, so that's interesting. Let me know if you figure out like what and why, kind of. I would just take it at face value then. So basically, a protic solvent promotes not really a Grignard reaction. Okay, so what happened here is that, yes, you guys all got it right in the chat. So what it came from was a cyclohexane that had a double bonded O, and then a triple bonded carbon came and attacked it. And this one only has one pathway. So it's important to recognize if there are two pathways and what those two pathways are, or if there's just one. That's important to know too. Okay, retrosynthesis. Ooh, this is going to be good. Okay, so we have a primary alcohol that turns into also a primary alcohol, but it has the addition of one more carbon. Okay. So this one is actually really, really interesting. So pay close attention. We have one more carbon in the end. So what we know is that there must have been a Grignard reaction in this. Because Grignards, when you have like a ketone, like let's say it was like this is an addition of one carbon right there when you use Grignard to attach it on. So, and this retrosynthesis is a little bit harder, honestly, from my perspective than the other stuff. Than like the, meta directing, whatever, activating, deactivating. This kind of stuff is a little bit harder. So, I'll just walk through this one and then we'll get a chance to do some more of them more together. But one of the things that you can do is you can kind of, because we know that this is going to be, it's going to have a ketone kind of happening in the end. So what it will look like is it'll probably look like there will be some step that has, the addition of one carbon. This is how you add one more carbon. And we need it to be like this. It can't have a Cl on it because then, because we need it so that when this attacks, it breaks off one of the bonds and that turns into an OH. That's very important. So, in order to get to that place though, first we're gonna need to make this into an MJBR situation, into a nucleophile. So how are we gonna do that? So one of the things that you'll have to note is PBR3, which we did a little bit last semester, but now it's like you're definitely gonna have to use it many, many times. So PBR3, what it does is all it does is that OH into a BR. And that's why it's so helpful. From there, we just do Mg over ET2O. And what that does is it adds an Mg on. So that becomes MgBr. And then from here, what happens is that now this is ready to be used as a nucleophile. So I'll take this here. So after this, what we've done is we've added one more carbon. So we can go ahead, add that carbon, and there's an OH at the end. But what he's showing here, which is interesting, is that basically it's not really an OH at this step. what's more likely to happen is that the MGBR are going to sit right here because we do have the MGBR that floated off of here. So it's going to be more likely to stick on to the O. And so in order,
Fatima,
yeah.
what is under the M? What's reacting with the Mg to get the MGBR? I can't read the
Oh,
handwriting.
sorry.
It's okay.
Yeah, it's ET2O.
Thank you.
No problem. So the last step, the final step that's going to get rid of that MGBR for good is just H3O plus. Because H3O plus is basically going to add a hydrogen to the O. Any questions? Okay. So an alternative synthesis that he shows right at the bottom involves epoxidation or an epoxy, but I don't think we should go over that yet because there's going to be a lot more about epoxidation to come in the next exam. So I don't really know if you guys need to know that right now. Yeah. Okay. So here's the one that we'll do together more. So benzene ring becomes benzene ring with, oh my God, so I'm just gonna redo a little bit. Okay. So this is what we get. Now, what do you guys think in terms of getting there? Where would our, like, what would be the Grignard that gets us there? Well, first tell me, where does the ketone belong to? I feel like there's multiple synthesis for this one. Yeah, there are definitely multiple paths. So here's one path that I can think of. So let's say that you did acylation first. If you took, yeah, there's lots of different things you could do. You could just take this, and it could have a double bond on it, Cl, and then AlCl3. And that would just attach to this position. And then that would actually be really quick. I don't know why he has this longer one here, but I'll show you guys some different options. And then what you could do is you could just have CH3 and GBr, and that would attack the Grignard position and become OH. So that's one option. Another option, which he prefers. So I think this is all about the pathways as well. Let's just take this for a minute and look at it closer. So where could our breakoffs have happened? So it could have come from something where it was like this, and it reacted with CH3 minus, or it could have come from something that was where this was the minus, you know, here, where this was minus, and then it attacked something that looked like this. So those are the two possible options. So actually, I think there's really only two pathways, really. So
Wait,
above,
isn't there like a third pathway that's like the same as the first pathway, but instead of having the extra carbon attached to the ketone, it's just attached to the Grignard?
which extra carbon?
So like there would be like two carbons attached to the benzene, which would be like the ketone, and then it would be like CH3, CH2 negative.
Oh, so you're
Yeah.
saying, yeah, but
Right?
the Mg, the negative charge would have to be here. No, yes, the negative charge would have to be there, right?
Wait, why can't you have CH2, CH3 MGBR.
At the end?
Yeah, like as the thing that's doing no. The other as in as a separate thing that is not attached to the
Oh, yeah.
benzene.
Yes. So you would have to, so you, if you had like this.
Yeah. Yeah.
But
And
these,
then a
oh,
ketone.
okay, but you still need the extra one here. No,
Wait,
that doesn't,
why?
wait, no, never mind. Okay, I see what you're saying. Sorry. Let me think about that for a second. Yes, that works. Okay, so there's 3 pathways. So, okay. So there's 3 pathways, and I already showed the let's give them numbers. Let's call this one number 1. Oops. Number 1, number 2, number 3. And what I did above is number is number 1. So let's just do number 2 real quick. So for number 2, what we'd need is we'd need certain product. Okay. Okay. So we would just need to take this and we need to attach a BR onto it. So that would be BR2, FeBr3, and then that would just have a BR on it. And then we would do our magnesium. And I'm hurrying up right now because we have not that much time left. This would become the same thing, but it would have an MgBr now. Now it's ready for Grignard. So from this position, all we'd have to do is use the ketone portion. So that would look like this. Yeah. What do I put in the bottom when I'm doing this? Oh, H3O plus. Okay. Okay, so that's pathway number 2. And then pathway number 3 is the similar thing. So, but instead our acylation step has oops. Okay, sorry. You can hear my roommates. Okay. So for this last step, we're just going to do acylation again, but this time we're only going to acylate 2 carbons on. So that becomes this. Then we're going to react this with MGBR. Okay. Okay. Any questions about that? So I think he would accept all of these equally. He would like them all. I don't really understand why he chose the number 2, which has more steps. Maybe because he wanted to show you a more complex way so you get more practice. Especially, it's important to have practice with bromination, stuff like that, of a benzene group. So that's helpful that way. And also knowing how to turn the BR into an MgBr. It's important. Okay. So some other stuff that, oh, this one is actually really good. So again, I just really want to bring this. I don't know why. I just have a feeling like this is something that might mess people up. So that's why I keep bringing it up a little bit. But when you have, here, sorry. Okay. So when you have a situation like this, when the first one comes in attacks, it breaks this off. When the second one comes into attacks it, it becomes an alcohol. So let's just practice it real quick. So the first carbon comes along, attacks it, breaks off. Second carbon comes along, attacks it, this goes up. So, and like some people, this is all you have to do on your piece of paper. Just draw 2 of them attacking so you can see what happens. And what do we get out of that? We get, now this has turned into an alcohol and it is attached to 2 methyls. That's it. Questions? All right. Okay, let's do one last example. Now, this one is interesting because what do they call this, guys? The CULI thing. I feel like I remember there was like a word for it when you use CU in particular. Okay, well if we see the word then yes, Kubrick or something like that. Yeah, something like that. Okay. So what this is a little bit different. Um, so if you see something like this, so it'll have a bracket. It'll have a bracket. And let's say inside the bracket there's a CH3. And basically on the outside of that there'll be a CULI. This part is like always the same. Whatever's in the bracket can change. So what this does is it kind of it substitutes one, oh sorry, there's two of them. There's always two of those things before the CULI. So one of these things gets substituted on to something else that had a leaving group on it before. So what I mean by that is that let's say I had something like this, okay? What we do is we take one of these, only one of them, and we'd substitute it onto this position, and the I would break off. So what does that result in? It results in this with an added carbon. This is our answer. Okay. And I know this is a little bit confusing, so I'm going to repeat it in just a second. Okay. So here's another example. Again, we have brackets, and let's say we have, I'm going to change it up a little bit. Let's say we have CH3, CH2, and there's two of them, and then there's CULI. So what happens when we take this and we react it with, I don't know, something? Okay, yeah, so he has an example like this. All right, so what happens is you take one of these from in here, not both of them. They don't both get substituted on. One of them does. So what that means is that it will just look like this now. Just one of them will come and it will attack here, and this will leave. And what does that result in? That results in this. All right? Okay, and this also, it doesn't have to be just with a leaving group, like it doesn't have to be with a halide. It can also work in a Grignard. So what do I mean by that? So let's say we have, let's make it a little bit more complicated. Let's leave it like this. So you can also do this if you want. Um, I like to do this as well because I don't always want to write things out in a condensed formula. So basically we have this portion and that's getting substituted. So what happens here is that, and for me, this portion is like, this is not another carbon here at the end. You know what I'm saying? Okay. So here in this case, oh yeah, this is the correct way to do it, sorry. So it's like this. Okay. So you can draw the bond line portion inside of the bracket and show that there's two of them. Now let's say that this reacted with something like this. Okay. So what that means is that this came along with a negative charge, attacked this carbon, this broke off, and what we got was we got the ketone is still intact because the first thing it did was it broke off the ester, and we have this on the other side. Okay. Any questions? Are you guys understanding this COLI stuff? Okay. Well, I guess we'll leave it at that for today. I don't think this stuff doesn't really look like it's going to come up on the quiz based on the practice quiz. Um, but it wouldn't hurt to go through it again if you have a nagging feeling that it might be on the quiz. Um, but yeah, we're basically done with this lecture anyways. So on Sunday, we are going to tackle the February 4th lecture notes, and we'll also go over the practice exam. Actually, no, on Sunday we'll do the lecture notes, and I'll take questions from the exam, but we won't go over the exam till Wednesday night. Actually, no, I take that back. Okay, so Sunday we'll do here. Because you guys will have another, yeah, so you guys will have so Sunday we'll do February 3rd, or sorry, February 4th, and we'll also do the exam. And then on Wednesday we'll do questions, Q&A. And then I might have a Monday session as well, and it'll probably be really short just for anything else that you guys want to go over, like a past quiz or stuff like that. Okay? All right. And if anyone wants any of the sessions recorded, let me know because I do that if you guys ask. All right.